mixed landfall here, it's the same thing that you will see that the convection is to the left. However, on the other case, where you have a storm in the other type, that you have very strong southerly shear, and so you expect the convection to the right of the storm. And similarly, for this case, it's the same thing, that the convection is to the right. So it seems that the vertical shear will also play a very strong role in determining where the convection should be relative to the direction of landfall. However, if you look at rain gauge data, we looked at rain gauge data that are over land. So if you look at the different rings, this is 100 kilometers, 200 kilometers, and 300 kilometers of the center of the storm as it makes landfall. What we found is actually that the rainfall is more to the right-hand side rather than to the left-hand side. Whether it is right at landfall or 50 kilometers from the coastline, you see that on the left front quadrant, generally the amount of rainfall is less than that to the right front. So apparently there's another, so in addition to the vertical wind shear, you also need to look at the topography of the system, of the land before it makes landfall. And this is very similar to the some of the model simulations by Tulea and Kurihara many years ago, in which they found that the storm before it makes landfall, it's to the left of the storm. This storm motion, each dot represents where you have the maximum rainfall. So you have more dots to the left before making landfall, but during landfall you have actually more dots to the right front quadrant, and that's very similar to what we have obtained from observations. And this is another modeling study that we've done before. This is the east of the storm, and the storm is moving from east to west, and so the storm is, if you can see it from here, that this is east, this is west, the storm is moving from east to west, and so you unwrap the storm like that, so you have, this is north, this is west, this is south, and so you go around here, and so before, this is the landfall time, so before the tropical storm makes landfall, this is the rainfall. The heaviest rainfall is to the southwest because the storm is moving from east to west, so it's to the left front of the storm. But after landfall, it's actually to the right front of the storm in our simulation. So I'll summarize here. The convection appears to be a very strong convection asymmetry prevalent. But it's not only related to friction and moisture differences, but also the vertical shear and topography. So I'll stop here. There is actually a flow chart, but I won't go into that. Thank you very much.
Okay. Questions? Chang-jae?
The impact from the land and ocean contrast may not be very significant from your calculation, but I find one thing very interesting with some insight. Because in Taiwan, there are many observations showing that from either satellites and surface station, all showing certain typhoons approaching Taiwan, they eventually turn left, and in many cases, went through the so-called Shuguranxi. That's the exit of a big river. And some people call that, well, with no scientific proof, it's a sucking effect from that river, the bank. It has a scale of about 10 kilometers. However, so I'm just wondering, maybe some of the insights you provided from your theoretical study can explain the shift toward the triangle bank in the riverside and of the exit of the river. However, the scale, it may not be correct because the scale in the real case of typhoon, the river is on the order of maybe 10 kilometers only, but the drip is higher than that. But in your simulation, you have the triangle area of more than hundreds of kilometers, and the drip is only like 20 kilometers. But I think this is an interesting insight. Maybe we can think about, or you can think about, to explain in the future.
Yeah, the delta that we have has a width of 100 kilometers and a depth of 150 kilometers. So it's very big. But I think you know, people have told me that along the China coast, in some rivers, there have been some anecdotal evidence that that the storms like to go along the river. Now whether it's true or not, we'll have to look at more data. But I think that what the result here shows is that whenever you have a friction or moisture difference, that will actually cause the track to change. Now whether it's because of the microphysics or other things, that we'll have to do more studies. But I think it's the idea here is that you would see that it's very important to be able to for operational forecasting. I think a message that I want to bring out from here is that in operational forecasting, a very important point is that in how you represent your land in your model is very critical in determining where the track is going to go. So if your land representation, like what I showed with very rough land versus less rough land, you will see that there is a deviation in the track. So if your land use representation in your model is wrong, for example, if it's supposed to be very heavily urbanized area, but then you represent it as farmland, then obviously the friction is, the roughness length is very different. So you would get very different results. So that's the lesson that I think we should think about when we do operational forecasting.
Whenever we have storms hitting that area, and the media always explain that as the sucking effect. In the future, I'll ask them to call you to ask for the explanation.
Okay. Yes.
Oh yeah, Johnny. So if you were to develop a parametric model to predict rainfall from tropical cyclone, certainly there's certain processes you'd want to incorporate. First and foremost is probably topography, also translational speed, and then like you said, vertical wind shear. And you showed results where you demonstrated the impact of surface roughness differences on the rainfall distribution. Is there a way that you could, how would you propose that you parameterize that impact in such a model?
For friction?
Yes.
I suppose you could use some, what we've done actually is to use the different roughness. So you can probably try to use that as a parameter in your forecast, that calibrate that with different types of roughness, or that would be one way to do it.
And would the degree of azimuthal shift be a function of the roughness difference? Perhaps something like that? I'm just trying to think.
Azimuthal shift, what do you mean?
Well, you showed the shift from primarily in the case, you showed an example where the rainfall was down to your left on the left side of the track of the storm, and then as it approached landfall, it shifted to the right side.
Yeah. Well, that will have to. One of the other parameters that you need to include that would be what I would call the angle of attack. If you use that the coastline and draw a normal to the coastline, and where the storm, where you expect the storm to make landfall relative to the coastline, that would be another parameter that you might want to put in.
Thanks.
Okay. We thank Professor Chan again.